So this is our second lecture video on electrochemistry, and I want to start off this video by looking at electrical current. And when we talk about the current of a liquid in a stream, we're discussing the amount of water that passes by in a given period of time. So here we have just this picture of the stream going through and the water flowing past. Well, we can use that analogy for understanding electrical current. So when we discuss electrical current, we are discussing the amount of electric charge that passes a point in a given period of time. So either as electrons flowing through a wire or ions flowing through a solution. So here we're looking at a spontaneous redox reaction between zinc and copper. And we have electric current flowing directly between atoms. And this is a redox reaction, and we have a current. And redox reactions involve the transfer of electrons from one substance to another. So when we transfer that electron, we get a current flowing. So in the beginning of this process, we actually have a zinc strip here. So it's a strip of zinc metal, and it's submerged in a copper 2+ sulfate solution. So if we look at that on the atomic scale, so we have the zinc metal ions here, so we've got the solid form here, and we have the copper 2+ ions in solution. What happens is that the zinc starts to give up some of its electrons. So as the zinc gives up its electrons, those electrons then combine with the copper 2+. So that makes copper metal, because we go from the 2+ to the 0 oxidation state, and as it goes to the 0 oxidation state, it wants to be more metallic, so it deposits on the surface of the zinc. And remember we said that the zinc gave up 2 electrons? Well, when that zinc gave up 2 electrons, it created a zinc 2+ ion. So here's a picture of it in solution. We start off with the zinc being inserted into the copper sulfate solution, and then over time, the copper that was in solution, the copper 2+, deposits as copper metal on top of the zinc. And one of the things that you should notice too here, look at the intensity of the blue color of the solution here versus the intensity of the blue solution here. This has a greater concentration of the copper 2+ ions, which means it's a darker blue color. But as we lose those copper 2+ ions and it goes to copper metal, the concentration of the copper 2+ is going down, so the color's lighter. Now, if we write this as a chemical equation, the zinc metal, so the zinc solid, reacts with the copper 2+ aqueous to form zinc 2+ aqueous and copper solid. So in this process over time, for 1 mole of zinc metal and for 1 mole of copper 2+, we are transferring 2 moles of electrons. So because we're transferring electrons, this redox reaction has the potential to generate an electric current. And in order to use that current, we have to separate the place where oxidation is occurring from the place that reduction is occurring. So we have to be able to separate the zinc portion and the copper portion so that we can capture that transfer of electrons. So a voltaic cell is how we separate out those two half reactions. And if you would watch the other video that we have for you on a voltaic cell, it does a really good job of breaking down the components of a voltaic cell. In this voltaic cell, we have zinc nitrate in solution, and we have a zinc anode. And this is going to be our anode, and the anode oxidation occurs. And the way I remember that is anode starts with an A, oxidation starts with an A. So at the anode, oxidation occurs. So if the zinc is going to be oxidized, it goes from zinc metal to 2+. And remember, oxidation is loss of electrons, so oil rig. Oxidation is loss of electrons, and reduction is gain of electrons. So as the zinc becomes oxidized at the anode, it makes zinc 2+, and it gives up those 2 electrons. Well, those 2 electrons then flow through our wires, and we have a light bulb here to show that the electrons are flowing. And the electrons complete the circuit and flow to the cathode. And the cathode is a positive terminal, and one of the ways I remember this is the T in cathode looks like a positive sign. So the cathode is the positive end, and at the cathode, reduction occurs. So cathode starts with a consonant, and reduction starts with a consonant. So at the cathode, you have reduction. So in this half reaction, we have copper nitrate and we have the copper metal. So the copper nitrate, the copper 2+ ions, take up the 2 electrons that were given from the zinc half reaction, and it forms copper metal. So there's just kind of a picture of what's going on. The zinc gives up its electrons, which flow through the wires and produces zinc 2+. And then those electrons flow through to the other side to the cathode, and those electrons combine with the copper 2+ in a solution to make the copper metal. So that's where we have the reduction. Now, as this reaction occurs, since the oxidation is producing a lot of 2+ ions in solution, the charge on the side is going to build up. So you've got a lot of 2+ charges building up as you produce more and more zinc 2+. And on the copper nitrate solution, you're using up a lot of 2+. So the copper 2+ is using up, the copper 2+ is being consumed, so that's leaving behind a lot of nitrates behind. So you get a negative charge being built up on this end. Well, if you get this charge building up, then the electrons can't flow just because you have a charge difference between the two cells. So to compensate for that, you have the salt bridge. And the salt bridge is a bridge that contains salt. So you have some kind of tube that's filled with your salt, so like potassium nitrate, and then there's a glass plug, so it keeps everything from just dumping into the solution. And so the potassium nitrate, the nitrate portion of the potassium nitrate will flow through to the anode end to balance out the positive charges that are building up. And the potassium end, or the potassium ions, will flow to the cathode side to balance out the negative charges that are left behind by the nitrate. So the salt bridge is there to balance out the charges in the two solutions to protect the electroneutrality between the two. Now, a common mistake that people make is they say that the electrons flow through the salt bridge. That's not the case. Remember, the electrons are flowing here through the wire. It's the ions that are flowing or move from the salt bridge into the solution. The nitrates, the negative ions, the anions, go to the anode, and the positive, the cations, move to the cathode. So since we're studying electrochemistry, we wanted to define what that is. Electrochemistry is the study of redox reactions that produce or they require an electric current. And the conversion between chemical energy and an electrical energy is carried out in an electrochemical cell. Spontaneous redox reactions take place in a voltaic cell, and that's what we looked at on the previous slide. And sometimes you may see those called galvanic cells. So galvanic cells and voltaic cells are synonymous terms. Now, if you have a non-spontaneous redox reaction, you can get it to occur by adding electrical energy. So plugging something up to an electrical source or a battery to provide enough energy to force the reaction to go in the reverse direction. So to make that non-spontaneous reaction spontaneous by adding electrical energy. So let's just discuss what electrochemical cells are. An electrical chemical cell contains an oxidation and a reduction portion of them, and they're kept separate. And these separated oxidation portions and the separated reduction portions are called half cells. So we have the oxidation half cell and the reduction half cell, and together they make the electrochemical cell. Electrons flow through a wire along with ions flowing through a solution which consists of the electrical circuit. And this is going to require a conductive solid, either metal or graphite electrodes, to allow the transfer of electrons. And those electrons are flowing through that external circuit. And there's also that ion exchange between the two half systems using the electrolyte. Now, as we start to use some of the terms like current, we also wanted to define what current is and what voltage is. And the number of electrons that flow through the system per second is the current. And the unit for that is the ampere. And 1 amp of current is 1 coulomb of charge flowing by each second. And 1 amp is equal to 6.242 times 10 to the 18th electrons per second. And the electrode surface area dictates the number of electrons that can flow. So the larger the surface area, the more electrons that can flow. Now the difference in potential energy between the reactants and products, that's the potential difference, and that's where we're talking about the voltage. And that unit is the volt. So 1 volt of force equals 1 joule of energy per coulomb of charge. And the voltage needed to drive electrons through the external circuit. And the amount of force pushing the electrons through the wire is called the electromotive force, or the EMF. So the voltage, that's talking about, like if we're referring back to our stream analogy of water flowing through, we can either have a large stream with a lot of pressure, so there's a lot of pressure in the stream, that's the voltage, but a lot of water passing by, that's current. Or we could have a small stream of water coming through with only a little bit of water coming through, but with a lot of force. So a little bit of water coming through, that's a small current, but with a lot of force, that's a lot of voltage. So hopefully that kind of helps you be able to internalize what this electrical chemical energy is and what current is, and what voltage is. Now the difference in potential energy between the anode and the cathode in a voltaic cell, that's called the cell potential. And the cell potential depends on the relative ease with which the oxidizing agent is reduced at the cathode and the reducing agent is oxidized at the anode. And the cell potential under standard conditions is called the standard EMF, or the E naught of the cell. And under standard conditions, we're talking about 25 degrees Celsius and 1 atmosphere for gases and a concentration of 1 molar for solutions. And then remember, this is the sum of the cell potentials for all of the half reactions. Now next we want to look at cell notation. And cell notation is just a shorthand description of a voltaic cell. As we look at the cell notation, we have 1 half reaction, so the oxidation half reaction is on the left, and the reduction half cell is on the right. And the first line here that we have separating here, we're separating the electrode and the electrolyte, so the solid and the aqueous. And here we have the aqueous and the solid. So the single line represents a phase barrier, and a double line represents the salt bridge. So we're showing the salt bridge here and the total separation of the oxidation half reaction and the reduction half reaction. And it's always oxidation and then reduction. So to help you remember this, O comes before R in the alphabet. So the oxidation occurs before the reduction. Or you can say the anode to the cathode, because the anode is before cathode alphabetically. Now, if multiple electrolytes in the same phase, then you use a comma to separate things out. So going back to that zinc copper cell. So remember we said at the anode the zinc was being oxidized, so it went from zinc metal to zinc 2+. So that's why we have zinc to zinc 2+. So we go from solid to the aqueous, and we have the lines separating those two phases. Now in this reaction at the oxidation, it's producing 2 electrons. So this is showing the flow of electrons from here to here. So since oxidation produces electrons, then the reduction consumes those electrons. So the copper 2+ takes those 2 electrons to make copper solid. And we see that in this reaction here. Now here's just an example where we have a multiple electrolyte system. So at the anode we have the iron being oxidized from iron 0 to iron 2+. But on the other end where we have the manganese, the permanganate ion, the MnO4-, the MnO4- is consuming 8 electrons and then 8 protons to make Mn2+ and 4 waters. So to write the cell notation, we have iron going to iron 2+, so that's the first half reaction, the oxidation. But at the reduction, we have the MnO4- separated with a comma, and the Mn2+ aqueous, and the H+ aqueous, and then the line to represent going from the aqueous to the solid phase, and the solid phase here is the platinum cathode. Now, as we start looking at the voltages, we have to be able to have some standard at which we're comparing those voltages to, and this is where we use the standard reduction potential. A half reaction with a strong tendency to occur has a large positive half cell potential. So the larger and positive the value is, the more likely it is to occur. And when two half cells are connected, the electrons will flow so that the half reaction with a stronger tendency will occur. And we cannot measure the absolute tendency of a half reaction. We can only measure it relative to another half reaction. So we select as the standard half reaction the reduction of protons to hydrogen gas under standard conditions. And we assign this a potential difference of 0 volts. So this is kind of like if we're defining altitude, sea levels are baselines. So we just say sea lines where we say 0 is, and everything is relative to that. That's what we're doing with the hydrogen electrode. So the standard hydrogen electrode is often abbreviated the SHE. So in this half cell potential, where we're measuring the half cell potential with the standard hydrogen electrode, we have the oxidation of zinc and the reduction of the protons to form hydrogen gas. So the zinc gives up its electrons. Those electrons flow through the wires to the switch. We measure the flow of electrons, or the potential difference, with the voltmeter. So the electrons flow through, and then those electrons combine with the protons in the water, so the acid, to make the hydrogen gas. Now if we compare the reduction potentials, zinc 2 plus has a reduction potential of minus 0.76 volts. And we said by definition the H plus has a reduction potential of 0 volts. So because the hydrogen has the larger, more positive value, the hydrogen is more likely to be reduced than the zinc 2 plus. So the hydrogen here is reduced, so this is why this is at our cathode, and the zinc is going to be oxidized instead of reduced. So if we measure the potential of the cell, the zinc 2 plus, this is for the reduction, is minus 0.76, but we want the oxidation of it. So the oxidation actually has a positive value. So the zinc going to zinc 2 plus 2 electrons has a potential of 0.76, because this is for the oxidation of zinc, whereas this value is for the reduction of zinc. And we said that the hydrogen was more likely to be reduced, so the 2 protons combining with the 2 electrons to make hydrogen gas has a reduction potential of 0. And we said this was the oxidation potential of the zinc. So when we combine these two together, we add the oxidation plus the reduction potential, we get the cell potential. And that cell potential is 0.76. And you can see this is what we read with our voltmeter. Now these values, when I looked up the reduction potentials of the zinc 2 plus and the hydrogen plus, I looked these up from tables. So I looked those values up from tables, and I'll show you in a little bit where those tables are and how to use them. But I first want to reinforce a couple of other concepts. Remember, the standard hydrogen electrode reduction potential is defined to be exactly 0 volts. And then half reactions with a stronger tendency towards reduction than the standard hydrogen electrode have a positive value for the reduction potential. And the half reactions with a stronger tendency toward oxidation than the standard hydrogen electrode have a negative value for the reduction potential. And the cell potential is a sum of the oxidation potential and the reduction potential. And if we're comparing one reaction and we have the oxidation of it, it has the opposite sign as the reduction potential is. So that's why when we did this reaction here with the zinc, and I looked up the reduction potential of zinc 2 plus is minus 0.76. If I write the reaction in the opposite direction, so going in this direction, it's a positive 0.76. Now, in the case where you're adding E values for half cells, do not multiply the half cell E values even if you need to multiply the half reactions to balance equations. So there's a big caution sign for you. So let's say you need to have 2 electrons, so you need to multiply through your chemical equation by 2, you don't multiply your E cell potential by 2, because you do not multiply those. They stay the same because the energy difference doesn't change. So here are our standard reduction potentials at 25 degrees C. So this is our standard reduction potential table. And what you'll find here, and I actually broke it up into 2 because this is a pretty long chart. So here at the top we have our stronger oxidizing agent. So fluorine is F2 is a very strong oxidizing agent because it itself wants to be reduced. So remember we said the more positive and the larger the value is, the more likely it is to occur. So the reduction of fluorine gas to 2F minus is very favorable. Now over here you have the weakest reducing agents. So the F minus is a bad reducing agent. It's not going to be a very good reducing agent. It's not going to want to go in the reverse direction. But the F2 is a very strong oxidizing agent. As we go down the table and see here's the hydrogen, so that's our 0 point that we defined. Something like lithium is a very weak oxidizing agent, but lithium metal is a very strong reducing agent because it wants to go in the opposite direction. So as we write these reduction potential tables, everything's written as a reduction. And we don't have to bother writing the oxidation because we know the oxidation reaction is just going the opposite direction with opposite sign. So we just list everything as a reduction half reaction in these tables. Now I will point out you're going to have to write a reduction half reaction table similar to this when you do the lab. A lot of people make a mistake in that when they do that because they don't write everything as a reduction half reaction and they don't put it with the most positive number at the top going to the most negative. So it should go in order from most positive down, decreasing to the most negative. And everything should be written as a reduction reaction.